Good morning to all of y'all. We usually talk about the moment of inertia of a thin ring or a thin rod. What if these objects were not thin, but if they were thick? And what do we mean by thickness? When we say thick rod or a thick ring, what do we mean by this thickness? To understand these questions, to answer these questions, we have taken a thin hollow cylinder of uniform density. The ring, the cylinder has a inner radius of R1 and an outer radius of R2. The length of the cylinder is L and the center of mass of the cylinder is O. We wish to find out the moment of inertia of this cylinder about an axis AA dash. AA dash is an axis passing through O and parallel to the two flat surfaces of the cylinder. So, what we shall basically do is divide this cylinder, cut this cylinder into slices, annular discs. We will have annular discs. So we will cut this cylinder into several thin annular discs. So to explain that, supposing we have this as the cylinder, this is the inner radius, this is the axis A dash, and here if we have a slice here at a distance x, and let the thickness of this be dx and its mass is dm. The complete mass, the total mass of the cylinder is capital M. So what we shall do is we shall consider an axis here b dash. Let the moment of inertia of this disc be di about the axis b dash. So we shall apply the parallel axis theorem to get the moment of inertia of that thin annular disc about AA dash, as di AA dash is equal to di BB dash, di BB dash plus dm into x squared. Yes, this is by the parallel axis theorem. Now, what is dm? The cross section is uniform throughout. So therefore, what we can say is that the mass will vary uniformly with the distance L. So the mass per unit length is a constant because the area of cross section is constant. So m by L is the mass per unit length into the thickness dx will give us the mass dm. Yeah. So dm is m by L into dx. Now, how do you find di with respect to the axis BB dash? Let us show that annular disc here. This is the annular disc here, and this is the axis B dash. What we shall do is we shall consider a perpendicular axis C dash in the plane of the disc and another axis out of the board D dash, and apply the perpendicular axis theorem. So we can say from the perpendicular axis theorem di BB dash plus di di bb dash plus di cc dash will be equal to the moment of inertia about dd dash. Now the moment of inertia about cc dash and bb dash will be the same because of circular symmetry. So therefore this can be written as di bb dash. So we can say 2 di bb dash is equal to di dd dash, or di bb dash is equal to di dd dash by 2. So let us see how we find the moment of inertia di dd dash. To do that, we shall divide this annular disk into several thin infinitesimal concentric rings. Supposing we show one of those rings at a distance r, and let us say the thickness of this ring is dr, and let its mass be dm dash. Yes. So the moment of inertia about dd dash, yes, if I call that as di dd dash for this ring, that would be equal to dm dash into r square, because every infinitesimal portion of the mass is at a distance r from the axis. So the moment of inertia of a particle we know is dm r squared, where r is the perpendicular distance from the axis. So this would be dm dash r squared. Now we know the total mass of this annular disk is dm. That is what we consider dm. So let us get dm dash in terms of dm. dm dash would be the density of this annular disk rho into the volume of this ring. The volume of the ring, the area of the ring will be 2 pi r dr, and its thickness is dx. We are saying this is dx. So into dx, that would be the volume. Yes. Now we divide. Let us get what is rho, the density. Rho, the density would be the mass dm of the entire disk divided by the volume of the disk. The volume of the disk is pi r2 squared minus r1 squared into dx. The area of the entire disk is pi r2 squared minus r1 squared. Yes. And the thickness dx. So you will have 2 pi r dr dx r squared. So dx would cancel, 1 pi cancels, and you have this as 2 dm r cube dr by r2 squared minus r1 squared. That would be the moment of inertia of this ring, of this infinitesimal ring. Now we need to integrate this. dm is a constant for the given disk. So when you integrate this, you will get di about dd dash for the entire disk. So you will have 2 dm and r2 squared minus r1 squared coming out. Yes, integral of this we are doing would be integral of r cube dr, limits from r1 to r2. Yes. So you will have basically here this is integral of di dt dash dash. The integral of this gives us di dt dash, the moment of inertia of this disk. So di dt dash should be 2 dm by r2 squared minus r1 squared into r power 4 by 4 from r1 to r2. So this will be 2 would cancel here, and you have basically dm by r2 squared minus r1 squared by 2 here, and you will have r2 to the power of 4 minus r1 to the power of 4. So that will be dm by 2 into r2 to the power of 2 plus r1 to the power of 2. That would be the moment of inertia di about dd dash. So the moment of inertia about dB dash. What is di about bb dash? We saw it is half of this. It was di dd dash di. You have di bb dash is equal to di dd dash by 2. So the moment inertia di bb dash would be dm by 4 into r2 squared plus r1 squared. That would be dvb dash. Now let us see what is the moment of inertia about the axis AA dash. About the axis AA dash, di AA dash is going to be di about bb dash, yeah, plus dm into x squared by the parallel axis theorem. Di bb dash is dm by 4 into r2 squared plus r1 squared, and dm x squared plus dm x squared. Let us write the expression for dm. dm was m by l into dx. So you are going to have basically dm as m by l into dx into r2 squared plus r1 squared by 4 plus m by l into dx into x squared. That is the moment of inertia of that annular disk, thin annular disk at a distance x from the axis A dash about A dash. This is about A dash. Now we simply need to integrate this. We have only one variable now, x, and x varies from minus L by 2 to plus L by 2. So if you integrated this, you will get moment of inertia about I A dash. So here you are going to get m by L. This is a constant, r2 squared plus r1 squared by 4. Yes, integral dx from minus L by 2 to plus L by 2 limits, and this one would be plus m by L integral x squared dx minus L by 2 to plus L by 2. So if we integrate that, what do we get? we will have I a dash is equal to integral dx is x, and if you put the limits r2 squared plus r1 squared by 4, if you put the limits, it will be from plus L by 2 to minus L by 2, and this is going to be m by L. The integral of x squared dx will be x cube by 3, and the limit is from minus L by 2 to plus L by 2. Yes. So this is going to be m by L into r2 squared plus r1 squared by 4 into L. The L will cancel, and you will have here m by L, m by 3L, and for x cube you will have L cube by 8 minus L cube by 8. So that is going to give us L cancels, and we have m by 4 r1 r2 squared, m by 4 r2 squared plus r1 squared plus m by this will be 2L cube by 8. So 2 will cancel with this 8. You will have L cube by 4. 4 into 3 is 12. L cube by L is L squared. So you will have ml squared by 12. That would be the answer of the moment of inertia. Now let us try to analyze this. First thing we would like to take is a thin ring. When you say it is a thin ring, what we are basically saying is that R2 minus R1 tends to 0, so that R1 is approximately equal to R2 is equal to some R, and this length also tends to 0. The length also tends to 0. That is, when you say thin ring, you have just this. This is a thin ring. So if you did that, if you put the limits here, what would be the moment of inertia? If you put R1 as R squared and R2 as R squared, you will have 2R squared, and this L tends to 0, so this term will vanish, and you will have a moment of inertia about this axis. Yes, about the diameter of the ring would be simply mr squared by 2. Yes. What if it were a thin disc? Supposing it were a thin disc, yes, R1, since it is a disc, R1 is 0. R1 is 0, and R2 is some R, and L tends to 0. Yes. So put R1 as 0 and R2 as R and L as 0. You will get the moment of inertia as mr squared by 4. That is a thin disc. Yes. What about a thin rod? You take a thin rod, yes, R1 and R2 both tend to 0 because it is a thin rod, so R1 and R2 tend to 0, and L is not equal to 0. So if you put R1 and R2 equal to 0, you will get the moment of inertia as ml squared by 12. That is for a thin rod. Now for a thin rod, we can say one thing. We have several thin rods stacked up. If you add one thin rod and another thin rod and another thin rod, so on stacked up, yes, if the masses are m1, m2, m3, etc., the total moment of inertia would be m1 L squared by 12 plus m2 L squared by 12, so on. So L squared by 12 will be common, and m1 and m2 and m3 all the masses will add, and you will get ml squared by 12. So in fact, whether it is a thin rod or whether it is a plate, thin plate, this is a thin plate of length L and mass m, the moment of inertia is going to be ml squared by 12. Yeah. The width of the plate, yeah, W or whatever you call B, the width of the plate will not matter. However long it may be, the mass will correspondingly increase, and the result is only ml squared by 12. Now let us take a cuboid. Let us say we have a cuboid. This length is, and we would like to find the moment of inertia about an axis passing through the center and perpendicular to two of the parallel faces. We would like to find the moment of inertia of this cuboid about this axis. Yes. Why we are considering this is because the cuboid can now be again approximated to a thin rod, and we will see those approximations. Let the length be L, let the breadth be B, and let the height be H. So what we do again here is slice this uh, cuboid into several square areas, square or rectangular areas. So I can slice this into rectangular, thin rectangular areas, thin plates rather. I can slice it into thin plates of at a distance x and thickness dx. And this is axis AA dash. We wish to find the moment of inertia about AA dash. So we shall consider another axis here, BB dash, passing through the thin plate. Find its moment of inertia about BB dash and apply the parallel axis theorem and get the moment of inertia about AA dash and integrate. So how can we do that? So you have basically if I show that slice, that thin plate, if I show that thin plate, the thin plate will have a thickness dx and a mass dm, and its height would be h, the same h, and this would be b. And we are talking about an axis like this, b, b dash. Yes. So the Moment of inertia of this above BB dash, above the axis BB dash, would simply be dm into the length b. The length becomes b here, into b squared by 12. That would be the moment of inertia about BB dash. We saw this result earlier. So di AA dash would be di BB dash plus dm into x squared. This is the parallel axis theorem which we applied for these two axes. Di BB dash is dm into b squared by 12. What is dm? dm, the mass will vary uniformly with length since the area of cross section is constant. So you will have this as m by L, right, this plus dm x squared. Let's substitute for dm. dm will be m by L into dx, b squared by 12. This will be m by L into dx into x squared. So let us integrate this. If you integrate this, you will get the moment of inertia about AA dash. You will have mb squared by 12L. Integral dx is going to be x. Yes. And this is going to be plus m by L. X squared dx would be x cubed by 3. Limits from minus L by 2 to plus L by 2. So, if you put those limits, IA dash is going to be m by 12L b squared, limits of x plus L by 2 and minus L by 2, okay, then plus the next term m by 3L into x cube, put the limits as L by 2 and minus L by 2, you will get L cube by 8 minus L cube by 8. So you would have mb squared by 12L, L by 2 minus L by 2 is L, plus m by 3L, this will be 2L cube by 8. So this L will cancel, this one L will cancel, and you will have mb squared by 12 plus this 2 cancels with this, and you will have ml squared by 12. So if you had a cuboid, like that, the moment of inertia, this is L, this is B, and this is H. So the moment of inertia about this axis AA dash turns out to be mb squared by 12 plus ml squared by 12. What you must note that H is missing in the expression, so it doesn't matter, the height of the cuboid will not matter because the axis is parallel to the height. Yes, if the axis had been parallel to the length L, then that L would be missing and you would have mb squared by 12 plus mh squared by 12. Yes. Now, if you are saying it is a thin rod, yes, this cuboid can be treated as a rod, and let us say it is a thin rod. Thin rod, we can say B tends to 0, so that it becomes a thin rod. If B tends to 0, the moment of inertia would be ml squared by 12. On the other hand, if we made it as a thin rod by reducing L to 0, by making L to 0, so that it is just a plate like this of height h and breadth b, and this is the axis. Then the moment of inertia would be mb squared by 12. Thank you.